Hello, everyone, and welcome to the CSAIL Forum. My name is Daniela Roos. I am the director of CSAIL, and today I am delighted to introduce our speaker, Professor Mohammad Alizadeh. Now, Mohammad got his PhD at Stanford, and he worked on revolutionizing computer networks. He has been doing that nonstop since he joined us as a professor at MIT. And for this work, he received numerous awards, including a Test of Time award, which is really remarkable for someone so young in his career. Today, Mohammed will talk about a human-inspired AI for system design and optimization. Now, before I yield the floor to Mohammed, I would like to ask all of you to please put your name and location in the chat so we know who you are and where you are. And please be an engaged audience and put your questions and comments in the chat. And with that, Mohammed, please take it away.
All right. Thank you, Daniela, for the introduction. And thanks so much for inviting me to participate. It's great to be with you all today. So I'm excited to share with you this work that we've been doing really maybe for about a year and a half at most, on a system called Glia, which is a human-inspired AI for system design and optimization. This is joint work with an exceptional group of graduate students and also my colleague and friend, Hari Balakrishna. So as you all know, AI is booming. And behind this boom is also a boom in AI infrastructure. So what do I mean by infrastructure? AI is delivered in huge data centers that house specialized hardware such as GPUs running complex software systems. And annual spending on AI infrastructure is just massive. It's expected to reach $1.2 trillion by 2030. And in fact, this may be an underestimate. In doing research for this talk, I found that McKinsey seems to think it's going to be $7 trillion by 2030, which just sounds like an insane number. But this is why NVIDIA is the world's most valuable company. But here's the problem. AI is actually outpacing its systems infrastructure. As models scale and AI applications proliferate, system infrastructure is increasingly becoming the bottleneck to progress. And we hear this repeatedly from companies, that scaling AI infrastructure is complex. Companies dedicate squads of engineers to optimizing AI systems, but even experts are overwhelmed by the challenge of achieving high performance, doing it cost effectively, and in the face of rapid change. So our vision and solution to this is a new form of autonomous infrastructure. We're building an AI called Glia, which architects and improves AI systems. Glia understands the characteristics of the workload, adapts to dynamic environments, and can continuously optimize across multiple layers of the software infrastructure to achieve performance and cost goals. And Glia designs and delivers these optimizations 10 to 100x faster than human experts, reducing weeks of effort to hours. Glia builds on more than a decade of research in our lab on AI-driven systems. So our group was among the first to apply AI, particularly reinforcement learning approaches, to challenging networking and system design problems. And we build AI-driven systems for many use cases, from video streaming to cluster scheduling, database optimization, and more. Building these systems taught us a lot about applying AI to systems, but these are really point solutions to specific problems. And it still takes a lot of expertise to design and more importantly, to operate such systems. But now with Glia, our goal is to build a more general system intelligence, as I'll describe. So to motivate the approach we're taking in this project, let me start by just examining how well language models can perform just out of the box at designing systems. And to be concrete, I'm going to use a specific example in language model serving systems throughout most of this talk. So LLM serving systems are systems that take requests from users, distribute them across GPUs, hosting different language models, and deliver responses back to users. And one of the key components in distributed serving systems is a request router, which decides how to distribute these inference requests among the GPUs in the cluster. So let's take a closer look at the request router. So the router decides for each incoming request which replica to serve it from. And these replicas may be running on heterogeneous hardware, like in this example, where some of these replicas are using, say, H100 GPUs, and some of them are using A100 GPUs. So as requests come in, for everyone, it has to decide which of these replicas to send it to. And what makes this problem, challenging is that the optimal algorithm here really depends on the characteristics of the particular workload that you're dealing with. So for example, if you take this snapshot of the system and ask where should this next request go, a generic algorithm like, say, least loaded queue, which sends requests to the inference engine, which is the shortest backlog of requests at any point in time, might say that this first replica is a good one. It has the smallest queue out of all the replicas. It's also running on an H100, which should be faster than the A100 GPUs. But the problem is that we don't really know how long the responses to the current requests are going to take to decode, because we don't really know the response lengths in advance. So it could very well be that this first replica is actually busy serving some very long request, and it's going to turn out to be slower than the others. So now that signal is something that's going to be very workload specific. So it's hard to come up with one size fits all algorithm that's going to use signals like this. So let me show you this sort of example prompt that we can use to ask a language model to design such a routing or load balancing algorithm for our system. So you can see we're asking it to design a load balancing algorithm. We're giving it a system model, which encapsulates our assumptions about the system. So here, we have some number of these, servers, and each inference job has two phases. There's a prefill phase and a decode phase, etc. We tell it what the objective of the problem is. Here we want to design an algorithm that minimizes, average latency across all these requests. And we give it like this function template that tells it, how it should produce a solution. So we can then sample solutions using our favorite language model, plug those solutions into an evaluation environment. For example, we use a simulator, and score these solutions. So in this chart, this score is essentially like the inverse of the achieved average latency. So higher scores are better. And you can see the scores for 3 human design baselines. These algorithms like round robin or least loaded queue These are default algorithms that are used in a lot of existing um, systems. And then this expert designed algorithm on top, that's an algorithm that I'll describe a little bit more later, but it's tailored designed for this particular workload in this example. And you can see it performs much better. So if we prompt, say, GPT-4o many times and plot the distribution of scores, this is what we see. So you can see, it's not bad. It performs many cases about the same or a little bit even better than the least loaded queue baseline. But it's still very far from this expert designed algorithm that was custom made for this workload. Um, Stronger, reasoning models are not much better. So this is O4 Mini, for example. And this is the O3 model, which, occasionally finds something a little bit better, but still it's pretty far from this expert designed algorithm. Now, this shouldn't really be that surprising. So even human experts can't really design systems in one shot the way we're asking here. Experts will implement their ideas, run some experiments, look at the results, get further insight about what ideas are promising. And this iterative experimentation loop is really what lets you improve upon these ideas. So fundamentally, we need a way to learn from previous experiments. So one way to achieve this is this approach called reinforcement learning fine-tuning, or RL fine-tuning. So the basic idea is you sample many solutions with a language model, and in tasks like this where you can score them, you can then use a reinforcement learning algorithm to fine-tune the language model to essentially shift the output distribution towards these stronger, better scoring solutions. And let me show you an example of this in action. So here we started from this Quen 2.5, 3 billion parameter model. And this is a relatively small model. So initially, it's not very effective at this task. Most of the initial solutions actually have an error, as you can see here. So these are solutions that didn't even run properly. But I'm going to visualize what happens when you do RL fine-tuning in this model. Before I start this, I just want you to kind of see that there's a small mass of solutions that actually are reasonable. They're about the same performance in this case as this least loaded queue algorithm. And notice what happens when the RL process starts. So the score distribution will shift, and eventually these stronger modes will get promoted. So most of the solutions end up being like these strong modes. And as you can see, this is continuing to improve gradually. Every now and then, there's sort of some kind of phase shift where another set of solutions get promoted. At the end of this, it actually found solutions that are about the same or even a little bit better than the top human designed algorithm for this thing. So this process of RL fine-tuning was actually able to find good solutions. But if you take a step back and think about this, the process is nothing like what a human would do, for such a problem. So this exploration that we just did here took 6,000 simulations. Whereas, a human expert working on this problem would probably find a solution in maybe tens of experiments. So this is very inefficient. And the final results are also often quite brittle, which I'll kind of get into a little bit later. So this motivates
Actually, Mohammed, can I ask you something?
Of course.
So with a reinforcement learning solution, you already said the solutions are brittle, but reinforcement learning usually looks at the solution in some context, looks at the task in some context. And so if you change the context, you need a new round of training. So
Yeah.
how do you think about that?
Yeah. So in what we did, I mean, here, this was kind of the the tasks were very narrowly defined as to, we're implementing this routing algorithm, a prompt like the one that I showed. And the environments, there's some variations that you can put on there, but it's sort of your RL fine-tuning for something that is trying to solve a particular type of algorithmic problem. And the what we found is that the the solutions do tend to overfit to the test scenarios, the training scenarios that you used. So like a human would inspect that solution and say, yeah, I kind of understand why it worked here, but there's some assumptions here about like sort of certain parameters that are unlikely to hold in other cases. Um, and we've seen that not just with reinforcement learning. We've seen that also, I'll talk about a little bit later, with some of these approaches that use like evolutionary style algorithms for code mutation. And these also end up oftentimes with kind of like solutions that don't look human-like. They have like a lot of if-else statements or many terms that got added at some point during the process. So what we tried to do with Glia was the kind of core thing is to ground the exploration um, in better reasoning from these experiments. And we found that that actually leads to solutions that tend to generalize a lot better. It's kind of less likely that you will, add like some random constraint or some random, parameter into your solution. Everything that the agent tries is grounded, and it has to have a very specific reason for doing it. And that we found to be quite effective. Um, so as I was just saying, Glia is designed to mimic the workflow that a systems engineer or a systems researcher would use to solve these problems. So it understands, the code base, it can read documentation, it can use the web, it can run experiments and analyze the results, and it can use this iterative experimentation loop to design new systems algorithms that are tailored to particular workloads and environments. So under the hood, Glia is actually a multi-agent system. Um, a supervisor agent provides an interface for human interaction and is also responsible for high-level project planning and giving high-level guidance to some of the other agents in the system. At the core of Glia are these playgrounds, which are often simulation environments. They could also, in theory, be test beds, but in many cases, we use simulation environments. And these are used for experimentation. So these playgrounds our vision is that they're created by playground builders that can calibrate them using telemetry from real infrastructure. And the workhorse of the system are these researcher agents, which can essentially perform design space exploration using these simulation playgrounds. So researcher agents, do their works inside these sandbox playgrounds, but they can also have access to external tools like search engines or solvers and so on. So let me give you an example of Glia in action, so you see how this works. I'm going to use the same request routing problem that I talked about. So recall that a lot of existing systems will have a few off-the-shelf algorithms like round robin or least loaded queue. And these generic algorithms will typically leave a lot of performance on the table. So in this example that I'm showing here, there's essentially a 30 to 50x increase in latency slowdown with these schemes when the system is running at high load. So latency slowdown is the latency of each inference request normalized to the lowest possible value that request could take. So normalized to the raw execution time of that request on the hardware. So a slowdown of 1 is optimal. And here you're seeing 30 to 50x increase in slowdown. By contrast, an expert design algorithm that's tailored to this specific scenario can perform much better. But it takes substantial expertise to come up with these optimizations. I mean, this particular one is actually something I worked on for about 2 weeks. It took me about 100 simulations. I'll show you what the ideas behind this are in a moment. But this is beyond the reach of most current organizations to sort of come up with ideas like this and validate them. So Glia actually discovers and verifies the same idea in simulation in about 2 hours of work. And you can look at this as better performance. You can also look at it as like shipping, these sort of AI applications much more cost effectively. So for example, this one optimization essentially lets you serve 22% more tokens while meeting the same latency SLAs as the off-the-shelf system. So let me show you how this works behind the scenes. So I'm going to switch over. So this is just the front-end UI, that we have for this agent. So I'm just going to start this. And you can see this is very similar to the prompt that I showed before. We're asking the system to design a request scheduler for distributed LLM serving, use the simulator in the current working directory to evaluate your ideas. There's a brief overview of the system. We have some number of replicas that can process requests, and the life of a request is as follows. We don't have to say too much because the agent will actually understand how things work by reading the simulation code base. The primary performance metric and objective, here we're optimizing this global scheduler, which is that request router, and the primary metric is the average response time of requests. There's an evaluation benchmark for it to test its ideas, and it's going to implement its ideas here. So as it starts, it sort of starts by, as I said, like reading the simulation code base. You can see it's kind of looking through the different folders. And then it starts reading like, what is this global scheduler class that I need to go write? What are the baselines like round robin and LLQ and so on? And eventually it's going to start proposing its own solutions to this problem and trying them. This entire process takes about 2 hours, as I mentioned, for this task. So I'm going to actually switch over here and just show you an example trajectory. So when the system starts, it reads the simulation code base and runs a bunch of these baselines to understand how things work. So here it's testing out the least loaded queue baseline. It then writes some Python code to process the results. And you can see, mean request end-to-end time is 40 seconds. So that's that horizontal line up there. That's what we're trying to improve by minimizing the latency. It runs a second baseline, and eventually it's going to give us its first attempt at the problem. So you can see it deletes this placeholder class for this scheduler that we had, and it implements a new algorithm with a lot of comments about what the idea behind this algorithm is. So for example, this first one is a simple algorithm that starts looking at the amount of free memory on the GPUs as an extra signal to the load balancing decision. So it goes out and implements that, then runs the simulation, analyzes the results. So that's trial number 1, and it's about the same performance as the baseline. And so then the search begins. In this initial phase, it goes through and implements many of the common techniques in the systems literature for this type of problem. So for example, the second attempt is essentially changing the scheduling order. So instead of a first come, first serve schedule, it prioritizes the shorter, the shorter request, the request with the shorter prompts first, which is kind of a typical trick for improving latency. Implements this, and it turns out it didn't actually work, at least in this first attempt. So I'll now fast forward. Every time you see a patch and like in a trial up there, these are again, in its initial phase, a lot of the standard ideas that you might consider for this type of problem. But as you see on top, none of these actually are really improving upon this 40-second baseline. And it turns out this is actually a pretty hard problem, and you need to go beyond these existing ideas. So let me show you how it ends up actually arriving at such a thing. So you can see we're about 100 actions in, 105 actions in. And this research agent says, I've carefully explored multiple design directions: memory over load balancing, prompt length bucketing, shortest prompt first, admission control, instrumented with the simulator. None of them achieve a consistent improvement over the baseline. So, we didn't like prompt it to try these ideas. Again, these LLMs have like read more papers than any of us. So these are some of the typical things that you would see in the literature. But here's where it gets interesting. It says, rather than continuing to iterate blindly, I'm going to step back, profile the baseline more rigorously, and derive a model of where time is actually spent. Is it queuing? Is it execution? Is it preemptions? Is it GPU memory pressure? Once that's done, we can target the dominant contributor directly. So this is sort of a very common thing that you would do as a systems researcher. It's like measure one level deeper to see what the actual behavior of the system is, what the potential bottlenecks are. And that's what it's going to do here. So you see it baseline LLQ run analyze. Here are the headline numbers. Again, the primary performance metric we care about is average end-to-end latency, which was 40 seconds. But you see, it measures a whole bunch of other things, like what is the scheduling delay? What is this thing called restarts, which is a problem that happens in these systems when GPUs run out of memory, and then the inference engine will have to evict some requests and try them again later. So you see, we noticed that like restarts are very high. 26% of requests were affected by restarts. Memory utilization was very high. And from these observations, for the first time, actually, it hints at this idea of maintaining headroom to curb preemptions and restarts, which ends up being a very key idea, and something that, when I was working on the same problem, after, some amount of time, at least after a few days, I kind of realized that the problem here, there is no load balancing signal that's going to really improve performance. There are periods where we're overwhelming GPU memory almost completely in the cluster, and we need a different mechanism, which is essentially you do congestion control. You stop scheduling and you throttle your rate of requests to match what the system can actually handle. And that idea is going to emerge a little bit later from this interesting interaction between this like two agents, this researcher and supervisor. So you see here, the researcher comes back and says, I implemented a bunch of other things. The best of them is 3% better than least loaded queue. And at this point, the supervisor agent intervenes and asks this interesting question. It seems we've been unable to reduce the number of restarts. Why is that? Is there something structurally wrong about our approach that is making it difficult to limit the number of restarts? And this is the kind of question that we might ask our PhD students working on a research project. And it leads to this like interesting chain of thought about why these restarts persist and what could actually cut them. And again, you see the first proposal is this idea of reserving headroom in the system. So for example, if for each replica, the GPU utilization was kept under 80%, this should eliminate restarts at the cost of some increased queuing. And so what I want to emphasize here is this really like human-like systems reasoning that is behind why the agent is trying the things that it's trying. And that is key. That's the thing that leads eventually to this breakthrough, which is an algorithm that Glia calls headroom admission global scheduler. I won't go through all the details of this, but it's essentially the same idea that when I was working on this problem, after a while, I found actually Glia's implementation is a little bit cleaner than the one that I did. But it replaces kind of a load balancer with something that will actually rate limit requests based on memory pressure in the system. And you can see it tries this idea, and the very first time that it tries it, actually, the performance metric of interest, latency, goes up. So we were at 40 seconds, now we're at 50 seconds. So like any kind of black box optimizer might give up or think that, oh, we made a mistake here. But again, this is very reasoning driven like process. So it actually started measuring restarts in the system, and it sees that that actually plummeted. So that went from like 3,000 to 7. And it knows that this means that it's made some progress. So it now starts doing some parameter tuning and refinement to this algorithm. And finally, that's actually when we have a breakthrough. And for the first time, we're below 40 seconds in terms of latency. And now it's found the right idea. So it kind of continues tuning this, and things get even better. And then finally, it composes this idea with this idea that it tried at the very beginning for prioritizing shorter prompts. And that gets us all the way down to 23 seconds average end-to-end latency, which is really about the same performance that I was able to achieve after 2 weeks of work on this problem. So let me get back to these slides. So this is the final algorithm that Glia discovered. And you can see, it's like 30 lines of Python code. This is something that, an engineer can review and understand exactly what it does and why it works. And again, there are two insights, specific insights in this. One is this idea of prioritizing smaller requests, and one is this admission control approach to limit memory exhaustion in the system. And this algorithm, actually, even though it was discovered in simulation, it translates very well to real hardware. So this is just a side-by-side experiment of the same scenario in simulation versus the cloud. And what you're seeing is the performance of this, the latency of these requests or slowdown at different levels of load. And you can see the trends all hold really well from simulation. And again, this is something that is quite interesting because a lot of these previous approaches that we worked on, like deep reinforcement learning approaches, when there's any kind of discrepancy between the simulation environment that you're using for training and the actual deployment scenario, typically they will fail quite poorly with DeepRL. But in this approach, because there's such a strong prior about the space of solutions that this agent will actually produce, it tends not to overfit to the particular training environments. The other thing that's interesting is that, once you have these playgrounds and an AI that can do things like this, you can throw them at many kinds of optimizations. So what you saw is just optimization of this request routing algorithm that I've been talking about. But then we asked Glia to turn to another subcomponent, which is this batch scheduler inside these inference engines. And it again found an interesting algorithm that reduces latency all the way down to 17 seconds. We then ask it to go after the autoscaler, and it comes up with this workload, kind of specific workload-aware autoscaling algorithm that gives us another boost in efficiency. So the end result in this example was that the stack that was optimized using Glia is about 40% more efficient in GPU compute hours to deliver the same latency as an off-the-shelf system. So we also compared Glia to a number of other recent approaches for using language models to design algorithms. Many of these are evolutionary approaches. So for example, OpenEvolve is a system, open source system based on the AlphaEvolve paper out of Google that essentially uses language models to sample solutions, score them, and then there's this evolutionary algorithm for essentially hill climbing the score function. So the kind of main difference between systems like that and Glia is, again, this very grounded exploration process that is using learnings from previous experiments to pick the next solution, as opposed to kind of a more black box evolutionary method for code mutation. And you can see in this result that Glia is more effective. So there's a few different variants of Glia here. SCG is essentially single context Glia. So that's just like one thread of exploration, just like what you saw in the demo. And you can see that this single thread is already about the same, or maybe even a little bit better than some of these evolutionary approaches. But if you take this and you just run it multiple times, and you do like a best of n strategy, then very consistently and reliably, you end up with stronger solutions than these evolutionary style algorithms. And you can take a closer look at that. So this is the trajectory of performance versus the number of experiments that the system ran. So what you want is, of course, in as few experiments as possible, you want to reduce this latency all the way down to this expert level. And if you look at the Glia curves here, like for example this magenta, you can see after about 40 experiments, it's already pretty much at the expert level performance, whereas these evolutionary approaches are still far from that, even after 100 experiments. We've also tried this on other problems and other workloads. So here's a different example where it's a very different workload that's very prefill heavy. So what that means is the prompts are now big and the responses are short, more like a chatbot sort of application. And in this case, again, Glia finds a new custom algorithm. It's a very different idea than the algorithm that I showed in my demo. Again, we've tested this on hardware, and then this gives us a pretty significant improvement in real deployments with H100 GPUs and the NVIDIA Dynamo system. So something like 5x latency improvements and about 15% throughput improvements compared to, again, an off-the-shelf system for this different workload. So before I conclude, I just want to sort of summarize. I think there's two key enablers and two requirements for a system like this. One is the ability to create these simulation playgrounds for evaluating AI proposals. And this is actually an interesting challenge in itself. Building simulators for these complex systems is difficult. Traditionally, simulators have to capture all these low-level details accurately, and then you hope from something that captures all the low-level details, you are able to create a model of the full system, which tends to be very difficult in systems like the one that I'm describing. I don't have enough time to go through this in detail, but our approach to simulation is actually quite different. We've developed a number of methods that you can start from this coarser grained system model, essentially modeling distributed systems as just networks of queues. And then you use trace data to improve the fidelity of these coarse grained models. So it's like an ML-enabled simulation environment. And if you're interested, there's a number of papers about this in the last few years, so you can look at those. And the second is how to build this agentic framework that guides AI exploration. So as I've been describing, these are difficult tasks. We can't just prompt an LLM and expect it to produce useful system optimizations. And the approach we're taking is this white box approach rooted in systems reasoning, rather than trying to sample solutions blindly with language models. So we designed our agent scaffolding essentially to try to teach the AI the workflow that we would take to tackle such problems, including what are the right questions to ask at different points in time, how do you design experiments, and as part of that evaluation environment, what are some of the guardrails that we need? So, this is a very kind of nascent, area. It's early days in this. There's a lot of research to be done. I've listed just a few of the things that we're actively thinking about. This question of how do you build playgrounds for AI for such problems is quite interesting. As I mentioned, our vision is that eventually AI should be able to build these systems playgrounds using real telemetry and real data from production systems. And it's also interesting to think about like what are some of the principles for verifying AI generated solutions. We found in our work that if these playgrounds are designed too narrowly, for example, the AI can come up with all kind of creative ways to cheat and come up with solutions that look like they perform well, but in reality they're not going to work. So, for example, caching and memorizing, the input examples, for instance. So there's a lot more work to be done in combating those and kind of systematically verifying solutions. Eventually, we're going toward these automated systems that are going to have AI essentially self-evolve, the system based on conditions. And of course, you have to think about robustness and safety. This has been a question for all of these AI-driven systems, work. But with language models and agents, the challenges are kind of quite different in my opinion. I mean, we don't have the same kind of overfitting type problems that we tend to see with deep reinforcement learning and those approaches, but we still need some kind of safeguards and fail safes for unexpected conditions, like if there's significant workload shifts or there are failures. Human AI collaboration is a really interesting topic in this area. So one of the strengths of this is really that it's a very explainable approach. And as I've seen, you can inspect what the agent is doing and see if you think it's reasonable. But we really need much better tools to enable human AI collaboration in these problems. And by contrast to some of the things that are out there, like coding agents, for example, one of the challenges here is that this process of design exploration is like inherently a very parallel, concurrent process. You might be exploring many ideas at the same time. And how do you even visualize that or kind of give information to a human collaborator so that they can have actually oversight and guide this complicated, concurrent exploration is very interesting. And then finally, the ultimate like North Star here, the vision is to create, AI systems generalists that like top experts can really learn about any system and start coming up with good insights and ideas about them. And we're not fully there. I mean, the system that I showed, I said, we don't prompt it to solve a very specific problem, but it is designed for a class of problems. Like we're doing resource management type problems in distributed systems. Whereas, again, a top human expert will be able to work across many kinds of different like systems and designing these architectures so that an AI can learn on the go is very interesting. So let me wrap up there. I think it's really time to use AI to build AI systems and AI infrastructure. And by way of analogy, if you think about hardware design in the 80s, it was really propelled forward by the CAD industry and tools like Magic and Spice that became really fundamental to how we think about hardware design. And I think that we're now at the point where software system design tools with AI, like Glia, could usher an era of exponential improvements for AI systems. So I will stop there, and thanks everybody for your attention.
Thank you very much. So I'm excited. We have time for some questions and discussion. And please stick around at the end of the talk. Get ready to unmute so we can give Mohammed a coordinated round of applause. We've been trying to do this at every CSAIL forum, and I look forward to getting it right. Perhaps today's the day. Okay, so we have some questions in the chat, and then I also have some questions, Mohammed. So let me start with a chat. Karen Solens asks, if I'm understanding this correctly, it seems that Glia is finding and optimizing against a single factor. Does that lead to the possibility of a local optimum? If so, is it possible or feasible to do a multi-factor optimization?
Yeah, that's a very good question. So the example I showed is absolutely the we had a single objective, minimize latency, but the system is not limited to that. You can um, do constrained optimization. You can do multi-criteria. We've done things like that. So, for example, we've done for this language model serving systems, a very typical optimization problem is you have a constraint on the latency, and then you're trying to maximize throughput or minimize cost. And we found that you can just describe that in natural language, and the models reason well enough about that that they know what to measure and how to think about it.
Okay. Okay, Tushar Krishna says, great talk, Mohammed. You brought up simulation fidelity of the underlying system as Glia is searching through its optimizations. I am curious if you ran into scenarios where Glia found solutions that worked well in the simulator but did not work well in an actual deployment due to the simulation model not being very accurate.
Yeah, very good question, Tushar. So we've uh, so this will become a little bit technical, but I'm sure you know this. So when we look at like prefill decode disaggregation, which essentially starts to introduce a lot more network communication, we found that there could be discrepancies between simulation and the real system. And that can lead to what you said, results that look good in simulation but don't actually perform well in the real system. It's very interesting that when we found things like that, um, we actually think there is a way of, again, calibrating our approach for simulation to those problems. But in a lot of those examples, we've actually found them to be bugs, essentially performance bugs in the real system that once you realize that, like, why that discrepancy exists, it's not clear that you really want your simulator to start modeling those issues. So we've been kind of looking at potentially using that, some of like extreme discrepancies as a bug finding tool as well. But in general, I mean, we have seen examples of what you said, where especially and I'm a networking guy, so this embarrasses me, but like a lot of the unexpected performance things tend to be because of network communication.
So, I mean, speaking of simulation, I just wonder, Mohammed, what do you think about using simulators philosophically? Most AI models do not understand the task nor physical constraints. Is simulation the right way to connect the foundational knowledge that's mostly symbolic into some physical reality? And is this something that works in in networking? Should we consider using this approach in other areas? For instance, we've used this successfully in robotics.
Uh-huh. Um, yeah, so simulation is I don't think simulation is fundamental to what um like an AI system designer or AI system researcher needs. you need some sandboxed playground for a lot of these problems. Simulation just turns out to be a very pragmatic approach for a lot of these things, especially when you're talking about the kind of like distributed systems problems that I'm describing here. Because building a test bed with a distributed cluster for the purpose of this kind of experimentation just maybe not practical, just too expensive. So it's sort of that's the primary benefit of simulation. But actually, this AI agent that I described, we have done applications where you connect it directly to a test bed, um, and you end up with some, like, you don't have the fidelity issues, of course, anymore. You end up with some other challenges, like around, for example, the code bases become more complex. So you have to sort of think more, about like the best practices for coding agents and all of those things. But I don't think like any of those stuff is really fundamental, like fundamental that you need you need a simulator. It just is um, it's a very pragmatic approach, especially for large scale system optimization problems.
So, okay, just to follow up on that, how should we think about the role of the human versus the role of the agent versus the role of the sandbox in configuring the algorithms of the future? If
Yeah.
the um, AI approach is much better at identifying an algorithm, how should we think about what people do in this area? And how do we get to solutions that are uh, task centric and causal as compared to most of today's solutions?
Yeah. So first of all, I mean, I don't want to give the impression that this right now is going to automate like system engineers or system researchers away. I mean, it's limited in scope, right? We're talking about like solving these heuristic like design problems. So for example, um, it is a lot harder to have this AI think about architectural issues in the same way, because in many cases it's actually not even clear that you can express them as clear like optimization problems with like verifiable scores or anything like that. There's a lot more involved in like making architectural decisions. So that's something that I think it's very interesting if we can get there where AI can do it well, but I don't see it yet. Um, and then even in sort of this kind of like performance optimization type problem, um, there's still, as I was saying at the sort of my last bullet with like this question of general system intelligence, I think we're still far from that. I mean, you still need to give a lot of guidance. The guidance is not in the form of um, like here's the particular like algorithmic idea to try, but the guidance, for example, is in the form of creating that playground that can verify solutions, knows what are all the properties that it should check, and pointing in the like the maybe the general right direction. So I feel like if you think of like different prongs of complexity, we are moving up in these prongs, but there's still like much higher level problems that humans need to be thinking about for the foreseeable future.
So let me go back to the chat. There is a question from Shamal Chandra, and this is about how this work is related to Andrei Karpathy's talk on Software 2.0 with program space. And so there's a reference to a Medium post from 2017, before the current onslaught of LLMs and Gen AI and
Yeah, if I remember correctly, I think this is sort of this vision that um, software design will become about writing verifiers, not like building software will become, if you can verify a solution, then AI can find it, which is kind of the philosophy that we're taking here. But with respect to, again, I think that is like a very sort of long-term vision for where we are trying to go. And we're trying to do that for these kind of system design problems, not software engineering, but system design. But even in stuff like this, which is kind of, I think, about the state of the art for using LLMs, we're still pretty far from realizing the full potential of that vision.
All right, final question from Manish Viswantan. Would you consider an AI automated evolutionary supervisor and a black box or random tester approach as a way to get better results? Or is that what you're doing already?
No, so we're not using an evolutionary algorithm in this system. Again, what we found is that for these problems, you really want the language model to have these coherent sessions of exploration. What I mean by that is that it's very important that you have like a sequence of, here's the idea that I tried, here's what I saw, here's now what I think about it, and continue. Whereas all these approaches that kind of use the language models in a more narrow way, as to like sample, like here's a prompt, here's some existing thing, can you evolve it to make it better? But then you don't create these coherent sessions of exploration. We found them that they can work, but it's sort of the comparison that I showed. Their success is a lot more ad hoc than what we were able to achieve in Glia. And then the quality of the final solutions, even if they all hill climb your score function, there's a qualitative difference between the kind of solutions that get produced using these methods. So even though, again, I think there may be definitely a place for a layer of evolutionary or a layer of kind of like some kind of black box optimization on top of what we're doing, I think this ingredient of having coherent sessions of exploration that are grounded in systems reasoning is important.
Mohammad, thank you so much for sharing your knowledge and wisdom with us. I'd like to ask all of you to please unmute yourselves. So let's try a round of applause. And so again, please unmute yourself. All right, and then on the count of three, let's all clap. Let's see. 1, 2, 3. Okay, it's getting better. Thank you so much. Have a great day, everyone. And this was the last CSAIL forum of 2025. We will come back with more exciting topics next year. Bye-bye.
Bye-bye. Thank you.